Okay, it's a great pleasure to have Professor Chang Liang from Nankai University to give a talk at our seminar this semester. He will talk about modular data of non-semisimple modular categories. Let's welcome.
Okay.
Please.
All right. First of all, I would like to thank Yilong to invite me to give a talk in BIMSA again. Okay. Um, Today I'm going to talk about our recent work on the modular data of non-semi-simple module categories. Well, it's um, yeah, we aim to generalize some very familiar result from the semi-sample category to the non-semi-sample category. Okay. At first, I will give a brief review on the background and then what is the s- key data in the module categories, and then I will talk about some generalization to the non-semi-simple module categories. And especially, I will talk about the examples from factorizable Hopf algebras. Um, okay, so the motivation from topology of our project is we can construct three manifold invariants from um, some semi-sample algebraic data. I think everyone should for familiar with the uh, the work from Witten and then Resting Drive and the Drive Wheel invariants. All of these construction are based on the semi-sample algebraic data, that is the modular tensor categories. Um, and then very recently, um, the semi-sample category um, turns out to be not enough to do the full manifold topology. That is, the semi-sample TKPs cannot detect the exotic smooth structure. We want to consider some non-semi-sample generalization of the TKPs and the modular categories. So I will first give a very brief review for the module categories, just to emphasize um, the points we want to generalize. So the module category is a Riemann fusion category, that is semi-simple categories with finite many simple objects, and we have non-degenerate braidings. And we can do the tensor product, and we have rigidities and the fusion rules. Then, yeah, the braiding just means we can switch to um, objects, and we have the Riemann structure that is natural isomorphisms. Um, so we can give link invariance for from the Riemann categories. Then in general, we can do the link invariance for Hopf algebras. That is one way to generalize the semi-sample structure to the non-semi-sample case. Um, the non-degenerate means um, when we look at the Hopf link, we compute the invariance, then we should get a non-degenerate S matrix. The Riemann structure will give us the T matrix, then the ST matrix um, will give projective representation for the SL to Z. modular group. Um, so and additionally, we will have the Voliner formula. We can compute the fusion rule from the S matrix, and another important result is the S matrix consists of the the algebraic integers. Um, well, and the kernel will be a congruence subgroup of the SL to Z. Um, based on this important result, then people prove that there are only finite many modular tensor categories with given rank. So so what we are going to do is to generalize the S matrix, the fusion rule, and also we will discuss the congruence. Okay, then so by a non-semisimple modular category, we mean some kind of non-degenerate ribbon finite tensor category. So here the category does not need to be a semi-simple category. We only need a finite tensor category. That means there might be some objects that they just indecomposable but not simple. Um, so um, so in this kind of categories, we can still do the tensor product, and we have rigidity, and we also have the braiding and the ribbon structure. The modular means um, when we do the double braiding, um, when we do the double braiding for x and y, if the x satisfying it's double braiding with any other objects y, we get the trivial double braiding, and the x has to be trivial. I think this condition is the same as the modular condition and in the semi-simple case. Um, so the modular data we want.
Hmm. I think he got disconnected.
Any question?
No, your video seems to freeze. So
Briefs?
yeah,
Uh,
you're not moving. So yeah, but anyway,
oh,
we can hear you. So yeah, good so
okay,
far.
it's okay.
Yeah.
Oh, okay. Yeah, I think the network is not good today. Well, okay. So in the semi-simple case, the rank is defined to be the number of simple objects. Now we want to count the indecomposable object into the rank. So we will call the rank to be the number of simple objects together with the projective indecomposable simple objects. Um, but there might be some intersection between the set of simple objects and the projective indecomposable objects. That is, there might be some objects, they they may be symbol objects. No, yeah, they may be symbol and also projective. Um, so for this kind of rank, we compute some examples. That is, we can still have the rank classification for only the total rank for the category of total rank up to 4. That is, if the rank is less or equal to 4, then we can show that this kind of um, modular categories are all semi-simple. And the next thing we want to generalize is the SL to Z representations. That is, um, we can construct um, a new that actually they are not new, but we can use the uh, Lobchenko construction for the SL to Z presentation representation to study some examples and get some hint for how to generalize the semi-sample module data.
So for the
Um,
rank, you you don't count twice, right? You if some object is projective, indecomposable, and simple, then you just count it
yeah,
once.
yes, yeah, yeah,
Okay.
yeah. Um, then for the fusion rule, we can consider some mixed fusion rule. That is, there might be some projective module, and we just do the tensor product between the simple object and projective object. And then they will give our um, some direct sum uh, among the projective modules. Then we will have a mixed fusion rule. Then for that mixed fusion rule, we can still have some kind of Welitter formulas. Okay, then let's first review for some um, some work for the non-semi-simple categories. That is basic. That is basically the work of Lobchenko. So in a module category, then um, w- we should have a coend. We should have a coend that is algebra in the category. Then by this coend algebra, Lobchenko constructed a TQFT. Um, that is 2 plus 1 TQFT. Um, expressed in so in this TQFT, then we can have a um, representation for the mapping class group. That is a closed um, for a closed surface. Then we will have a vector space that just the Hopf space from the tensor power or that from the tensor power of the coend to the unit. Um, in in particular, the the tollers will give us um, the modular transformation. That is, we get um, S and T transformation. That's from the Hopf space um, of L and the tensor unit to itself. Then the S and T satisfy this kind of relation. They the relation are almost the same as the relation of SL to Z, except that the S square equals the inverse of the antipole. So from this relation, we can see if we consider the representation category of factorizable ribbon Hopf algebra, then the coend is the same as the dual of the Hopf. Um, then the Hopf space from the coend to the tensor unit just the same as the center of the Hopf algebra H. Um, so when we restrict it on the center, the previous ST transformation will give us the SL to Z representations. That is the uh, uh, on the center. That is on the center. We will have the S to the fourth power is identity. Identity. Um, Yeah, on this slides, we just write down the transformation in a formula with the R matrix and the ribbon elements and also the integral of the Hopf algebra. So
What is kappa?
kappa is some constant, just some constant.
Okay.
Okay, so by factorizable ribbon Hopf algebra, we just mean we have uh, braiding, a non-degenerated braiding, in the sense that when we do a double braiding in the Hopf algebra, that is, we can write down the dream field map um, with the double braiding, then we will get a linear isomorphism from H star to H. Um, so with this dream field isomorphism, um, we can actually identify the center of H with the Q trait, the Q character of H. Now the Q character just means it's almost like a trace. That is, we use the antipole squared to twist the trace. Um, so the reason why we want to consider the factorizable ribbon Hopf algebra is that we will have an analog of the S matrix. Um, so for this, we can take a look at the link invariant defined using Hopf algebras. So if we have a ribbon Hopf algebra, then Hennings and Kaufman and Raffold define a link invariant. Um, so for example, the when we look at the Hopf link, um, and we we can take two copies of the R matrix, then we can label the factor of the R matrix on the components of these two circle. Then we can multiply the components along each components along each circle. Then um, and then we get two product for each circle. We get product for each circle. Then we use the integral of the Hopf algebra to do the evaluation. Then we can write down the link environment for this Hopf link. Well, then if the Hopf algebra is factorizable, then this environment can be simplified. Then we will get the result just equal to um, integral acting on the co-integral. Now the little lambda is the integral in H star, and the big lambda is the integral in H. So um, a result from Hopf algebra um, tells us the value of the little lambda acting on the big lambda is not equal to 0 if the H is factorizable. Um,
Uh, so the
oh,
last not zero, not because it's factorizable, right? The
yeah.
G square vanishes.
Yes, sorry. The factorizable, well, so the factorizable um, means the capital lambda equals the image of little lambda of the dream field map. That is in the formula. Um, if we want to get the big lambda from the FQ of little lambda, then we need the condition of factorizable. So the last inequality not equal to 0 just because we we are considered finite dimensional Hopf algebra. Yeah, it's not because the factorizable. Okay, thank you. So we can see from this example um, the factorizable condition will give us non-zero link invariant of the Hopf link. So yeah, I think that's the reason why we consider the factorizable Hopf algebra is a kind of generalization of the non-degenerate uh, ribbon the ribbon category. Um, so yeah, in our work, we make some particular calculation for the factorizable ribbon Hopf algebra, and um, we get some particular results, and we hope this kind of particular result um, should be generalized to the general case. So the first example we considered is the UQSL2. Um, so uh, so in the slides we can see the algebraic and the Hopf algebra structure, and then it has the R matrix and the ribbon elements, and also we have the Q characters. Okay, then and so um, yeah, just we have seen on the center, we should have the SL to Z representations. Then Thomas Kerr um, first wrote down a decomposition of this SL to Z representation. So he he first make this decomposition as a conjecture. Then we give a detailed verification for this decomposition. It says Um, for the center of the SL2, for the center of UQSL2, the SL to Z representation decomposed into two parts. Um, the There is one part looks like um, a standard representation, that is the 2 by 2 matrix of the SL to Z representation, and tensored with a semi-simple representation of the SL to G. That is the V part. That part is just the same as the SL to Z representation obtained from the Rustigin 12 TQFT. Um, the-
U12. Third.
of the UQSL2.
Uh,
Um,
can you repeat again? After stating the theorem, you disconnected a little bit.
okay. Yeah, I said the representation decomposed into two parts. Yeah, one part um, is the tensor product between the standard uh, two-dimensional representation and the semi-sample uh, representation from the sticking 12 TQFT. And then the other part um, we will call the non-semi-sample part. Um, it is written as the pH plus 1 in this decomposition. This part is the same as the Higama ideal of the UQSL2. Um, well, the Higama ideal, let me see. Okay, let me explain more detail about the Higama ideal. So, so we have seen that there there is a isomorphism between H star and H. Uh, and then there is another isomorphism between H star and H for any finite dimensional Hopf algebra um, that is given by Rafford. That is, we take a integral capital lambda from H, then um, we will have the phi from H star to H. Then um, with these two isomorphisms, we get we actually have two isomorphisms from the Q characters. Actually, it should be yeah, from the Q characters to the center. That is FQ um, will maps the Q character to the center, and so is phi. Then for the UQSL2, we actually um, have this decomposition. That is, the image of the FQ and phi um, of the Q character will be full of the center of SL2, UQSL2. But they are not, but these two images are not um, are not destroyed. That is, these two kind of images um, have intersection, and this intersection is exactly um, the p parts in the decomposition. And it turns out this intersection part um, are all from the Q characters of the projective UQSL2 module. And and then so that is the general description of the Higgs ideal. That is in general, when we look at a Hopf algebra, actually, I think, Hopf algebra, then we take the Q trace for our projective modules. Then, um, then under the Raffold isomorphism, we will get the Higgs ideal. We get the Higgs ideal.
So
Um,
is are both Greenfield isomorphism and Radford isomorphism
mhm,
isomorphisms of H modules?
yeah.
Yes. Okay.
Well, so first for if we just have a finite dimensional Hopf algebra,
Yeah.
then um, we will have Raffold isomorphism. Then we take the image of Raffold isomorphism for the Q character of projective module. Then we get Higgs ideal.
Okay.
Then uh, if we have um, factorizable braiding, then we will have another isomorphism, the Drinfeld isomorphism. Then um, we will have the Higgs ideal in another way using
Yeah, I know. I'm
the
just
Drinfeld
asking
isomorphism.
if the Radford isomorphism, an isomorphism of H modules，它是不是那个 H map？它是你有个 H action 吗？
Um, well,
它
I
是 H
think
module map
in
吗？
general, um, H map. Probably not. I don't think it is H mod.
But Drinfeld isomorphism is right.
No. Drinfeld isomorphism just a linear isomorphism.
Not H module.
I mean, the Drinfeld map just give you an isomorphism for vector space.
Oh, okay.
Yeah. Okay. Um, okay. Then um, yeah. Then we can decompose the SL to Z representation into two parts. Then the um, the semi-simple part um, is given by these two matrices. Think they are the same as the ST from um, the string 12 TQFT, that is from the um, SU to module categories. Then the ST matrix from the Higgs ideal part um, is given by these two ST matrix. Uh, then from this two matrix, yeah, I think yeah, from this two ST and ST matrix, we can write down the fusion rule. We can write down the formula for a mixed fusion rule. That is, um, if we look at all symbol objects and the projective in the composable objects, um, then we can define a mixed fusion rule for the Q characters. That is, we can multiply the Q character of symbol object with the Q character of the projective in the composable objects. Then the product will be decomposed as the sum of the Q character of the projective modules. Then the coefficient can be computed using the um, S matrix uh, from the S matrix. Um, then this can be considered as non-semisimple generalization of the Wallin formula. Um, okay. Um, so yeah, when we look at the exact reform for the ST matrix in the previous decomposition, then we can see um, the semi-simple part and the non-semi-simple part of the SL to Z decomposition will give us an SL to Z representation from some pointed modular categories. Then um, from this, then we can have the congruence property, that is the SL to Z representation on the Higgs ideal is also a congruence. I mean, the kernel is also a congruence subgroup of the module group. Okay. Yeah, this result is obtained by a particular calculation. So in general, we hope um, this still to be true for a general ribbon Hopf algebra. Then another example we have computed is the double of um, the so-called Nichols Hopf algebra. Well, this Nichols Hopf algebra is not the same as the classical. Um, I mean, I think that there's another more famous Nichols algebra from the classification of pointed Hopf algebras. But here, by Nichols Hopf algebra, we mean um, the following Hopf algebras. Actually, it's just some kind of smash product um, between two very simple Hopf algebras. That is, we do a smash product. Um, we do the smash product between the um, a, a group algebra and the exterior algebra. Then we get the following relations. Um, then this Hopf algebra is not factorizable. So in order to get a factorizable Hopf algebra, we just take the double, take the quantum double. Then we get a factorizable ribbon Hopf algebra. Um, um, but here this Hopf algebra is not ribbon yet. So only when the n is um, when the n is even it's ribbon. So in the following we only consider the n is even. Um, so we we continue to compute the representation category for this double Nichols. Then it turns out it has two irreducible objects, irreducible module, and um, uh, yeah, there are two irreducible modules of dimension one. And then um, there are two other irreducible modules of dimension 2 to the power n. Um, so the 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 two irreducible module of dimension 2 to the power n um, are also projective. So there are totally six, um, I think, bases. So there are totally six basic objects. Um, so the total rank of this representation category is equal to six. Um, is equal to six, but the fusion rule, the mixed fusion rule for these objects are very different when we look at different n. So for different n, the module the representation categories should be not equivalent. That means we have examples. We have examples for the finite rank finiteness. That is, we don't have the rank. It's a counterexample for the rank finiteness. That is, for a different n, we have a non-semisimple module categories of total rank 6, but they are all not equivalent. Then we just do the same thing as the UQSL2. We computed the SL2Z action on the center. Then we found the center also decomposed into two parts. Again, there is a part as the is the Higma ideal part. Then the other part is a direct sum of the tensor product of a bunch of the standard representations. So the standard representations appears again as a tensor product factor. So in general, we just yeah we just um, guess there might be some similar decomposition, and then in one part, there should be a standard representation appeared as a tensor factor. Then yeah, I think yeah, that's the main work we have done. That is, we will yeah, we want to make a generalization of the semi-sample modular category to the non-semi-sample sample categories, and we make a calculation on examples and hope to have some I mean insight on what the structure is in the non-semi-sample module categories. Then I think yeah, I think that's all I want to say. Thank you.
Thank you very much for the nice talk. Let me first stop the